Dear students, our lesson is System of Particles and Rotational Motion. In the previous videos, we considered systems of particles. Now, from now onwards, we will be considering rotational motion. And we consider rotation about a fixed axis. Let us consider some examples. Here, symmetric top is rotating about its vertical axis. Our earth is rotating about a fixed axis connecting north pole and south pole. Ceiling fan is also rotating about a fixed axis. This is axis of rotation. Here this is axis of rotation. Here this is axis of rotation. And if you take wall clock, the hours hand, minutes hand and seconds hand, all these are moving in dial plane, and the axis of rotation is perpendicular to the plane, perpendicular to the dial plane. So like this, all these are rotating about a fixed axis. Now let us take a general diagram here. See, this is x-axis, this is y-axis, this is z-axis. Suppose this object is rotating about the z-axis. Now if you consider a particle inside the body, when the body is rotating about z-axis, the particle describes a circle around the axis of rotation. So this is the circle described by the particle during rotation. And a vector from here to the particle, this vector is called radius vector and represented by r bar. This is radius vector. As the particle is rotating about the axis, at time t the particle is here. At a time t plus delta t, that means what? After delta t seconds, the particle came here. So it moved through an angle delta theta. So this is called angular displacement. See how we define angular displacement. The angle through which the radius vector representing the position of a particle rotates is called angular displacement. Its SI unit, radian. Angle is measured in radians, that you know. It's a dimensional formula, m power 0, l power 0, t power 0. It means it is a dimensionless quantity. Now, see here, as the position of this particle moving on a circle is changing with time, the particle possesses angular velocity. Angular velocity is taken or defined in two ways. One is the average angular velocity, another is instantaneous angular velocity. See, in general, angular velocity is defined as the rate of change of angular displacement is called angular velocity. Now, in particular, average angular velocity is defined as delta theta by delta t. It means what? The time taken for the particle to move from here to here is delta t. So in delta t time, it moved through delta theta angle. In 1 second, it moved through how much angle? 1 by delta t into delta theta. See once again, let us see here. As the position of the particle is changing with time, moving on the circle, we say this particle possesses angular velocity. And this angular velocity is defined in two different ways. One is the average angular velocity, another is instantaneous angular velocity. So here let us define the angular velocity in general. See, if it is linear velocity, how we defined the rate of change of displacement is called velocity. Rate of change of displacement means linear displacement, but here it is angular displacement. Therefore, rate of change of angular displacement is called angular velocity. Now, in particular, average angular velocity. This is defined as omega is equal to delta theta by delta t. See here, the particle is here at time t, and after delta t seconds it came here. It means in delta t seconds it moved through delta theta angle. If in delta t seconds it moved through, it had a angular displacement of delta t in 1 second. How much? 1 by delta t into delta. So in 1 second it has undergone this much angular displacement. That is called average angular velocity. So rate of change of angular displacement is called average angular velocity. Next, instantaneous angular velocity. This is defined like this. Limit delta t tends to 0, delta theta by delta t is equal to d theta by dt. So what is the difference between here and here? When finding average angular velocity, you take a certain time interval, a finite time interval. But when you are calculating instantaneous angular velocity, the time interval is taken very small. That is the difference here and here. Okay, now whether angular velocity is a vector or scalar. Angular velocity is a vector. It means it has magnitude as well as direction. Then in which direction it has? What is its direction? Its direction is given by right hand rule or right handed screw rule. Let us see here. This is right handed screw rule. If you move anti-clockwise, the screw moves up. See here, this body is moving anti-clockwise. Therefore, the angular velocity will be upward. If it is moving clockwise, the angular velocity will be downward. So in this way, we use right-handed screw rule. There is another rule, that is a right hand rule. This is our right hand. This is our right hand. The fingers, if our fingers show rotation direction, thumb represents angular velocity. See here, it is moving like this. See, it is like this. Therefore, thumb upward. Omega is upward. Suppose let us consider this wall clock. Here, hours hand, minutes hand and seconds hand. These are moving clockwise. And if you take a screw and if you move it clockwise direction, it moves down. Therefore, omega here will be perpendicular to the paper plane but directed downwards. Like this, it is directed downward. Now, considering its SI unit. See, in the numerator, angle is there. In the denominator, time is there. Angle is measured in radians, time is measured in seconds, so radian by second. Now coming to dimensional formula. For the angular displacement, there is no dimension because this is a ratio. See, angle in radians is defined as angle in radians is defined as arc length by radius. Arc length is L, radius is L, L gets cancelled. Therefore, m power 0, L power 0, T power 0 for angle. Okay, for angle there is no dimension, but time it is T and this is in denominator. When taken to the numerator it becomes T minus 1. So m power 0, L power 0, T power minus 1. Like this we consider. When a body performs n rotations in a time interval t, then its average angular velocity. See, generally we write omega is equal to delta, average angular velocity is defined as d theta by dt. But here it is making n rotations in time t. So here delta t, in place of delta t you write t. Okay, in this much time it is making n rotations. One rotation is equal to 2 pi radians. N rotations. How many? N by 1 into 2 pi. So 2 pi n. So here you write 2 pi n. One rotation gives an angular displacement of 2 pi radians or 360 degrees. So n rotations make how much angular displacement? N by 1 into 2 pi. So in time t it is making n rotations. So in n rotations it is moving through this much angle. Therefore we write the same thing here. So in such cases we use this formula. Now let us do this problem. Find the average angular velocity of the seconds hand of a watch if the seconds hand of a watch completes one revolution in 1 minute. So Whenever data is given in revolutions or rotations, we use the formula for average angular velocity. Omega is equal to 2 pi n by t. Here n is number of rotations per second. Number of rotations in time t. So, okay. How many? Only one revolution. Time 1 minute 60 seconds. So omega is equal to 2 pi into 1 by 60. Radians per second. Now let us consider another problem. Find the average angular velocity of the spinning motion of the earth. So here for earth, it is spinning around its own axis. Earth rotates once in 24 hours. It takes 24 hours time to complete one rotation around its own axis. So number of rotations 1, time taken 24 hours. 24 into 1 hour means 60 minutes. One minute means 60 seconds. So average angular velocity 2 pi n by t. 2 pi into 1 by 24 into 60 into 60. So in this way we get the answer. When a motorcyclist takes a U-turn in 4 seconds, what is the average angular velocity of the motorcyclist? So this is a straight ride. Here he is taking U-turn, moving in this direction. See here, suppose east, west, north, south. He is traveling eastward. So here it is moving like this and going in west direction. It means from east to west. By how much angle he moved? 180 degrees. So here also we can see the same thing. See, like this is coming. So if you show the radius vector, it is like this. So it moves through 180 degrees or pi radians. So the delta theta is equal to pi radians. Time 4 seconds. So average angular velocity is equal to delta theta by delta t. That is equal to pi radians by 4 seconds. Radian per second. Linear velocity is denoted by v. Angular velocity is denoted by omega. Now let us derive a relation between linear velocity and angular velocity. First let us obtain the relation in scalar form. Let us consider this figure. A particle is moving on a circle. In delta t time, it is undergoing some angular displacement here. So here this is the distance traveled. This is distance traveled on the circle, and this is the position vector. This position vector is, okay, now R is the radius of the circle. Okay, now let us write angle in radians is equal to arc by radius. Angle in radians theta, arc, so this is the arc length S, radius R. By cross multiplying we get S is equal to R theta. Now differentiating with respect to time. Differentiating with respect to time, ds by dt is equal to, see, radius is constant, d theta by dt. Now distance by time gives speed. Rate of change of angular displacement is, so this is angular distance by time, so this gives angular speed, so V is equal to R omega. This is the relation. So V is linear speed, omega is angular speed. So V is equal to R omega is the relation between linear speed and angular speed. So the relation between these two is in the scalar form. Now let us obtain the relation in vector form. See, here particle is moving in a circle. If a particle is moving in a circle, its angular velocity will be along the axis of rotation. Okay, and along the axis of rotation, whether upward or downward. To decide that, we make use of right-handed screw rule. See, according to right-handed screw rule, in which direction it is rotating? Anti-clockwise. If its head is rotated anti-clockwise, it will move up. Therefore here, as the particle is moving anti-clockwise, the omega or angular velocity will be along the axis of rotation upward, because it is anti-clockwise. Therefore upward, omega upward. Now omega cross R is equal to omega cross R means OP. R means OP is equal to omega cross OP means it is a sum of this vector and this vector. OC plus CP gives OP. Okay. Now by distributive property, because cross product obeys distributive property, therefore omega cross OC plus omega cross CP. Now here omega cross OC, omega and OC both are in same direction. If they are in same direction, theta is equal to 0 and sine 0 is equal to 0. See, since omega and OC in same direction, theta is equal to 0, sine 0 is equal to 0. Therefore this becomes 0. Therefore omega cross OC is equal to 0. So omega cross R is equal to omega cross CP. This is omega, this is CP. So this can be shown like this. Let us shift this omega vector upward. This omega shifted upward. So this is omega, this is CP. This is omega, this is CP. Now omega cross CP means from omega to CP, you imagine screw moving clockwise. If it is moving clockwise, it will move forward. So it will move in the direction of V. Therefore this becomes V. It is like this. Omega cross P means if it is moving clockwise, screw moves forward, velocity also forward. Therefore omega cross Cp becomes velocity. So V is equal to omega cross R. So this is the vector relation. Next, angular acceleration. Rate of change of angular velocity is called angular acceleration. So average angular acceleration alpha is equal to delta omega by delta t. So omega stands for angular velocity. So rate of change of angular velocity with time is called angular acceleration. Next, instantaneous angular acceleration. This is limit delta t tends to 0, delta omega by delta t is equal to d omega by dt. So in this way we define, and its SI unit. See, first of all, this is a vector, this is a vector, and second, its SI unit is, see, it is angular velocity and its unit is radian per second. In the denominator, second is there, so therefore radian by second square. This is SI unit, and its dimensional formula will be m power 0, l power 0, t power minus 2. So this is about angular acceleration. Next, see here. Here we have derived a relation between linear velocity and angular velocity. Let us see here the scalar form v is equal to r omega. V is equal to r omega. V is linear velocity anywhere. See here the linear velocity. Here the linear velocity v. See anywhere. So r is radius vector, omega is angular speed. See, if we take, suppose if we take a fan, suppose we take a fan, it is moving, it is rotating. So suppose you select a point here, suppose it makes 3 seconds to complete one round. You select another particle farther from this. So as fan moves, this particle describes a larger circle. Even though this describes a larger circle, it takes same time to complete one rotation. Why? Means this particle and this particle are on the same blade. Therefore, whether it is a nearer particle to the axis of rotation or farther particle to the axis of rotation, it takes the same time to complete one rotation. It means the angular velocity is same. This particle, this particle, this particle, any particle will have same angular velocity, angular speed. So this is constant. This is constant. So if this is constant, v directly proportional to r. If distance increases, linear velocity also increases. And one more thing, if r is equal to 0, v is equal to 0. It means r is equal to 0 means on axis of rotation. R is equal to 1 meter, r is equal to 2 meters, r is equal to 3 meters. Here r is equal to 0 meter. Means on axis of rotation, when you take r is equal to 0, v becomes 0. So the axis of rotation is not moving, it is at rest. So like that. See, we had kinematic equations for linear motion. What were they? V is equal to u plus at. Second, s is equal to ut plus half at square. What was the third one? V square minus u square is equal to 2as. So here the kinematic equations are valid only when a is constant. When a is constant. So these are the equations for linear motion. Similarly, let us derive kinematic equations for angular motion. Now let us derive kinematic equations for rotational motion about a fixed axis with a uniform angular acceleration. That means alpha is constant. See, previously for linear motion the equations were like this. U was initial velocity, V was final velocity. But here, instead of U and V, let us show like this. Linear velocity is shown as V naught plus CAT is equal to V, like this. V is equal to V naught plus CAT. V naught means initial velocity. This is initial velocity at t is equal to 0. This is final velocity at t is equal to t. So just like that, let omega naught is initial angular velocity at t is equal to 0 and omega is equal to final angular velocity at t is equal to t. Now, by definition, angular acceleration is nothing but rate of change of angular displacement, that is d omega by dt, or d omega is equal to alpha dt. Integrating the equation, see, omega is changing from, angular velocity is changing from omega naught to omega. Here alpha means angular acceleration, that is constant. You write outside. So dt. Time is from t is equal to 0 to t is equal to t. Now here if you integrate d omega, you get omega. If you integrate dt, you get t. Now upper limit substituted minus lower limit. Upper limit minus lower limit. So omega minus omega naught is equal to alpha t, or omega is equal to omega naught plus alpha t. This is the first kinematic equation. Now let us derive second kinematic equation. For that, by definition, omega is equal to d theta by dt, or d theta is equal to omega into dt. Now integrating the equation, d theta is equal to omega dt. Here angle is moving from theta is equal to 0 to theta. And here omega, see in the first kinematic equation, what was the first kinematic equation? Omega is equal to omega naught plus alpha t. So let us substitute this here. Plus alpha t dt. Now integration of omega naught dt plus integration of, see alpha is a constant, let us write outside. So here t remains t dt. Here omega naught is a constant, dt plus alpha t dt. Time changes from 0 to t. d theta changes from theta 0 to theta. If you integrate d theta, you get theta, upper limit theta, lower limit theta naught, omega naught constant. If dt is integrated, you get t. If t is integrated, you get t square by 2, t 0. Now theta minus theta 0, t minus 0, to bring outside t square minus 0 square. We get theta minus theta 0 is equal to omega naught t plus half alpha t square, or theta is equal to theta naught plus omega naught t plus half alpha t square. So this is the second kinematic equation. See, actually theta minus theta naught gives angular displacement, that is delta theta is equal to omega naught t plus half alpha t square. In linear motion, angular displacement is replaced by linear displacement, angular velocity replaced by linear velocity, and here initial, 0 means initial velocity. So here initial linear velocity u t plus half. This is angular acceleration, this is linear acceleration t square. So in the same form it is there. Okay. Now let us derive third kinematic equation. By definition, angular acceleration is rate of change of angular displacement. Angular velocity. So here let us write this as d omega by d theta into d theta by dt. D theta gets cancelled, we get the d omega by dt here. Now d omega by d theta into d theta by dt means rate of change of angular displacement gives angular velocity omega. So now cross multiplying, we get omega d omega is equal to alpha d theta. Now integrating. Here alpha is a constant. If we integrate omega, we get omega square by 2. If we integrate d theta, we get theta. Here omega changes from omega naught to omega. Angle changes from theta naught to theta. Therefore here upper limit omega naught, theta, theta naught. So here 1 by 2. So omega square minus omega naught square is equal to alpha into theta minus theta naught. Or omega square minus omega naught square is equal to 2 alpha. Theta minus theta naught means angular displacement. See, this is the third kinematic equation. See here, and in the linear motion, here comes v square, here comes u square, here comes a linear acceleration, and here comes, in place of angular displacement, we get linear displacement. That's all.